In this video, we're going to start taking the ideal gas law, which is PV equals nRT, and expanding that to think about other systems, such as a system of combined gases, or interpreting other information about gases. In this case, we're going to start to think about predicting the behavior of gases. We want to think about what is the density of a gas, what is the molar mass of a gas, i.e. the molecular weight of the gas, and how does a gas behave within a mixture? So what is the partial pressure and how does that work? So the ideal gas law is conducted at standard temperature and pressure, otherwise known as STP. For gases, this is 273 degrees Kelvin, otherwise known as 0 degrees Celsius, and 1 atmosphere. So typically, if we think about PV equals nRT, we could come in and solve for 1 mole of gas using the ideal gas constant. We could solve for V, where V is equal to nRT over P, for equal to 1.00 moles multiplied by 0.08206 liters atmospheres mole Kelvin, multiplied by 273 Kelvin, divided by 1 atmosphere. And when you do that, you would get that the ideal volume of an STP is 22.4 liters. So this is the molar volume. When people think about STP, it is, or the standard conditions, it's 1 mole of gas, 22.4 liters of gas, 1 atmosphere, and at 273 degrees Kelvin. So what else can we do to think about this information? So we can start to think about the density of gases. When we think about the density of a substance, we know that there are substances that float and substances that don't. We can think about a solid that has a higher weight than another solid, and that density makes sense. But we're going to start to think about the density of a gas. So we can think about the density of helium. We know, or we've observed, that a helium balloon floats. There are often instances where people use a container of SF4, and we know that that gas is quite heavy, so things can float on top of that gas. It makes it look like they're suspended in air. But we're going to think about the density of gases, and we're going to be able to calculate that using the ideal gas law of PV equals nRT. So we know that density equals grams per mil, or more often grams per liter. So if we have PV equals nRT and we need to get to a mass divided by a volume, we can think about N divided by V, which gives us P over RT. And we need a way in order to get this density value into grams per liter. So this would have been moles per liter equals atmospheres over liters atmosphere mole Kelvin. So what we're actually going to do is multiply both sides by the molar mass, where the molar mass is in grams per mole. And so this is going to give us moles over liter multiplied by grams per mole, which is going to give us atmospheres grams per mole. Oops, this should be a multiplied sign, over liters atmospheres moles Kelvin times Kelvin. And so in this case, we can now derive this equation. So this is the density of a gas in grams per liter, and then we're going to have the pressure. This is the molecular weight. R is the ideal gas constant, and T is the temperature in Kelvin. And so we just need the molar mass or the molecular weight in order to find the density. So let's look at an example. So if we want to calculate the density of chlorine gas at 125 degrees Celsius and 758 millimeters of mercury, we want to use the fact that the density equals the pressure times the molar mass, RT. So the pressure in this case is 758 millimeters of mercury. We're going to convert that into atmospheres by dividing by 760 millimeters of mercury. And that's going to give us 0.997 atmospheres. We have a temperature of 125 degrees Celsius plus 273, and that gives me 398 Kelvin. We're going to use the standard R value, in this case of 0.08206 liters atmospheres mole Kelvin. And so the only thing left to determine for this is the molar mass. And so for chlorine gas, so chlorine comes as a diatomic, so it is 2 times 35.45. And so that gives you 70.90 grams per mole. So in this case, we are going to plug all of these values in of 0.997 atmospheres multiplied by 70.90 grams per mole. Divide that by the R value of 0.08206 liters atmospheres mole Kelvin. Multiply that by the temperature of 398 Kelvin. And so when you plug this into your calculator, I get 217 grams per liter as the density of chlorine gas at 125 degrees Celsius and 758 millimeters of mercury. So we can use this in other types of calculations. So if in this case we know that the density of a gas is 1.43 grams per liter at 23 degrees Celsius and 0.789 atmospheres, what is the molar mass of the gas? So we're going to use the same equation where D equals P RT, but this time we want to solve for M, where that is dRT over P. And so we know that the density is 1.43 grams per liter. We know that R is 0.08206 liters atmospheres mole Kelvin. We have a pressure of 0.789 atmospheres, and we have a temperature of 23 degrees Celsius plus 273.15, and in that case is going to give you 296.2 Kelvin. So now we can plug this all into our equation of 1.43 grams per liter multiplied by R, 0.08206 liters atmospheres mole Kelvin. Multiply that by our 296.2 Kelvin. Divide that by the pressure of 0.789 atmospheres. When I plug this all into the calculator, I get 44.0 grams per mole. And you could imagine situations from earlier videos, such as the empirical formula or other instances where you could use additional information to determine the molecular formula for this. But in this case, it's just asking for the molar mass of a gas, keeping in mind significant figures. So we can start to think about determining the molar mass. So in this last calculation, we solved for the script M. So in this case, we're not going to have the density. We're going to use PV equals nRT and try to come up with the molecular weight, which is essentially grams per mole. And so in this example, a sample of a gas has a mass of 0.311 grams, a volume of 0.225 liters at 55 degrees Celsius, and a pressure of 886 millimeters of mercury. What is the molar mass? So the molecular weight is grams per mole. We have a grams, and that could go here. And we could divide that by N, which is the moles. So we could solve for N equals PV over RT, and then divide the mass divided by the moles, because this amount, 0.311 grams, corresponds directly to the amount of moles in this calculation. So we have a volume of 0.225 liters. We have a temperature of 55.0 plus 273.15, and that gives us 328.2 Kelvin. Oh, and we have a pressure of 886 millimeters of mercury divided by 760 to get it to 1 atmosphere, and that gives us 1.17 atmospheres. So now we can plug this into our calculation of 1.17 atmospheres multiplied by 2.225 liters divided by our R value of 0.08206 liters atmosphere mole Kelvin multiplied by our temperature of 328.2 Kelvin. So this gives us 0.00978 moles. So the molecular weight is going to be grams per mole. So we're going to take our 0.311 grams, divide that by 0.00978 moles, and this gives us 31.8 grams per mole. So now we can combine both the density or other information in order to determine and identify the gas in our component. So now we want to think about mixtures of gases. So a mixture of a gas is essentially if we have a container of gas, and inside this container we have several different gases. We can have this gas, we can have a lot of this gas, and then we're going to have a little bit of this. So if we think about the space occupied, we can see that the green gas occupies the most. One of the things we need to think about is how does each gas contribute to the total pressure? So if we know that we have a single container, we can start to think about each gas independently. If we think about the blue gas as gas A, we know that the pressure of A is equal to the moles of A times RT over V. This is just using PV equals nRT. We know that the same is true for B, where PB is equal to NB RT over V. And same for the yellow, where the pressure of this is equal to the moles of that, RT over V. So if we were to want to think about the total pressure in this system, P total, which is the total pressure, is equal to the pressure of A plus the pressure of B plus the pressure of C. So all of these pressures add up to one another. So we could also rewrite that as NA plus RT over V plus NB RT over V plus NC RT over V. And this is all in one container, so they all have the same volume and the same R value and the same temperature. So we could rewrite that where NA plus NB plus NC multiplied by RT over V is going to equal P total. We could also realize that P total is equal to N total times RT over V. So the partial pressures of all of these components are going to be adding up to the total pressure. So each gas contributes based on the moles of the gas, and we can see that in these different calculations. So let's think about how we could use this information and what other calculations we could get. So if we wanted to look at the pressure of A, so if we just wanted to look at the pressure of A, which is equal to NA over RTV. If we wanted to think about the partial pressure or think about the relationship between the partial pressure and the total pressure, where PA divided by PT is going to equal NA RT over V divided by NT RT over V. So these are going to cancel out to where the NA divided by N total is equal to PA over PT. So the pressure of A is equal to the Na over Nt multiplied by the total pressure. This right here is called the mole fraction. And we tend to annotate that as the Greek letter X, so chi A. This is the fraction of the gas we'll call this the fraction of the total gas for any given component. And because the pressures are additive, we know that the mole fraction of the gas directly corresponds to the total pressure of the gas. So these two equations over here on the right, where the partial pressure of A is equal to the mole fraction of A times the total pressure, where the mole fraction of A is the moles of A divided by the total moles of the system. So these calculations can be quite long when we start to think about this. So let's look at some examples for the partial pressure and the mole fraction. So the first thing we're going to think about is if air is 78% nitrogen gas and 21% oxygen gas. The remainder percentage, because 78 plus 21 is only 99%, is a mixture of argon and carbon dioxide. So if the system is at 1 atmosphere, what is the partial pressure of N2 and O2? So the P of N2 is equal to chi of N2 times P total, where chi of N2 is the fractional component of the percentage. So that's 0.78 multiplied by 1 atmosphere, and that gives you 0.78 atmospheres. So P of O2 is going to be equal to chi of O2 times P total, which is going to be 0.21 multiplied by 1 atmosphere, and that's going to give you 0.21 atmosphere. So we could do this provided you know additional information, and you can imagine these calculations could be as complex as having two masses and adding those together, or having different information. So in the first example, we have a 1 liter mixture of helium, neon, and argon, and has a total pressure of 662. So P total is 662 millimeters of mercury. And we have a temperature of 298 Kelvin. So if the pressure of helium is 341, so PHE is going to be 341, and the pressure of neon is equal to 112, what is the mass in argon of the mixture? So in this calculation, we need to figure out the pressure of argon so that we can then put that into N equals PV over RT, where we have the pressure of argon, the volume of the system, the R value, and the temperature. So we can determine the pressure of argon, so PAR, is going to be equal to the P total minus P helium minus P neon. And so that would be 662 minus 341 minus 112. And so I get 209 millimeters of mercury. And we're going to go ahead and divide that by 760 to get that into atmospheres. And so that's going to give us 0.275 atmospheres. So now we are going to go ahead and, sorry about the movement, solve for the moles of argon. So N of AR is going to be equal to the pressure of 0.275 atmospheres, multiply the volume of 1 liter, and divide that by the R value of 0.08206 liters, atmospheres, mole, Kelvin. and multiply that by the temperature of 298 Kelvin. So we get a mole value of 0.01125 moles of argon. Now it asks for the mass, so we need to convert this into grams. So we're going to take our 0.01125 moles of argon. In 1 mole, there are 39.95 grams, and that gives me 0.449 grams of argon. Now, in this case, we didn't use the chi value because we didn't know the moles of either helium or any of the other components. So we're going to have to, in later examples, start to think about those components. So in this case, a gas tank, which is 7.12 liters, is filled with 8.18 grams of N2O and 12.1 grams of SF6 at 21.1 degrees Celsius. Calculate the mole fraction and partial pressure of each gas. So the first thing we're going to do for each of these gases is calculate the number of moles, because in order to calculate the partial pressure, remember P of A is equal to chi A times P total. So in this calculation, we have neither chi nor the total pressure. So we're going to have to be able to solve this. And there are several different ways you could do this. You could calculate the pressure for both and then add those together to give you the total pressure. Or you could use the total moles in order to calculate the total pressure and then solve backwards. Regardless of the way that you look at this, you can do this either way. So in this case, I'm going to take my 8.18 grams of N2O, divide by 44.02 grams in 1 mole. So that gives me 0.1858 grams of N2O. We're going to do the same thing for SF6, so 12.1 grams of SF6. I'm going to divide that by the molar mass of 146.07 grams in 1 mole. And that gives me 0.08284 grams of SF6. So in this case, if we add these together, in total is going to be 0.26864. So I can now find P total. So P total is equal to N total RT over V. So we can start plugging these in, 0.026864 moles times the R value of 0.08206 liters, atmospheres, mole, Kelvin. Multiply that by our temperature. We're at 21.1 degrees Celsius. Plus 273 is 294.25, which is going to round to 294.3. And I'm going to divide that by the volume, in this case, which is 7.12 liters. So now we can get the total pressure of 0.9107 atmospheres with sig figs is 0.911 atmospheres, which is going to be P total. So in order to calculate the mole fraction and the partial pressure, we are going to use, for N2O, P of N2O is equal to chi of N2O times P total. And in this case, we're asked for both the mole fraction and the partial pressure. So chi of N2O is equal to 0.1858 divided by 0.26864, which is 0.6916. So the pressure of N2O is 0.6916 multiplied by 0.911, and that gives you a pressure of 0.630 atmospheres is the pressure of N2O. So now we're going to do the same thing for SF6, where the chi of SF6 is equal to 0.08284 divided by 0.26864. And that gives me 0.3084. So the pressure of SF6 is equal to 0.3084 multiplied by 0.911. And that's going to give me 0.02. Whoops, that's not right. Now we have 0.281 atmospheres. It's important to note a couple of things. These two pressures add back up to 0.911, and you could have subtracted the mole fractions from a value of 1 to give you the total mole fractions. So when we think about partial pressures, we have to keep in mind both the moles, the total moles, all of the information about these situations in order to calculate the partial pressure of any given gas.